Welcome to the deep dive. Today, you're joining us as we really dive into one of the most fascinating things in the universe, black holes.
Absolutely. We've got quite a mix of sources here.
Yeah.
Wikipedia pages giving that broad overview, but also a university lecture on general relativity, which gets into the nitty-gritty physics.
And even that NASA simulation, right? Visualizing what it might actually be like to fall into one, which is mind-bending.
It really is. And the sources, they take you on this journey, don't they? From the basic ideas, the almost unbelievable properties, how they form.
Yeah. And how we even know they're there, plus the big, big questions they still leave us with.
Mm-hmm.
So our mission today really is to pull out the key insights, those aha moments for you, without, getting totally lost in the weeds.
Sounds like a plan. Where should we start?
Okay, let's start right at the beginning. When we say black hole, what fundamentally is it?
Well, simply put, it's a place in space-time, an incredibly dense place, where gravity is so powerful that nothing can escape, not even light.
Nothing at all.
Nope. Once you cross a certain boundary, we call it the event horizon. That's it. You're pulled in.
Wow. And, it feels like such a modern sci-fi concept, but our sources mention this idea goes way back, doesn't it?
It does, surprisingly far back, like late 18th century. Jean-Michel and Pierre-Simon Laplace, they had this idea of dark stars.
Dark stars?
Yeah, based on Newtonian ideas, they figured if something was massive enough, its escape velocity could be faster than light itself. So light couldn't get away.
So the seed of the idea was there even then, but it really took off with Einstein, right? General relativity.
Exactly. Einstein completely changed the game. He showed that gravity isn't really a force pulling things across space.
Right. It's about mass and energy actually warping space-time itself.
Mm-hmm. Mass tells space-time how to curve, and space-time tells mass how to move. Like the Earth isn't being pulled by the sun exactly.
It's following the curve in space-time caused by the sun's mass, like rolling a marble on a stretched rubbery sheet with a heavy ball in the middle.
Precisely. It follows the straightest possible path, a geodesic, through that curved space. And a black hole is what happens when that curvature becomes, extreme.
Okay, extreme curvature. Let's get into the structure then. The event horizon you mentioned, that's the boundary, the point of no return.
Yeah, think of it like a one-way door in space-time. Cross it, and there's no turning back. You're heading towards the center.
And the center. That's the singularity, isn't it? That sounds intense.
It is. Theoretically, anyway.
Yeah.
According to general relativity, the singularity is a point of infinite density. All the black hole's mass crushed into zero volume.
Infinite density, zero volume. That sounds impossible. Like our understanding breaks down there.
And it does. That's where general relativity sort of gives up, We think quantum mechanics must play a role at that scale, but we don't have the full picture yet. It's a huge puzzle.
Right. So the singularity is this theoretical endpoint inside. But from the outside, black holes are actually simple. I read about the no-hair theorem. What's that about?
Ah, yes. The no-hair theorem. It's a catchy name.
Mm-hmm.
The idea is once a black hole settles down, you can describe it completely using just three things.
Only three. What are they?
Its mass, its electric charge, and its spin, its angular momentum.
That's it. So all the details of whatever collapsed to make it or whatever fell in, it just vanishes.
From an outside observer's perspective, yes.
Yeah.
All that complexity, all those details, the hair is lost. We only see mass, charge, and spin. It's kind of profound, really.
It really is. All that drama ending in just three numbers. So, are there other important regions? I think I saw mentions of a photon sphere.
Yeah, there are a couple of other interesting zones. The photon sphere is outside the event horizon. It's a region where gravity is so strong that photons, light particles, can actually orbit the black hole.
Light orbiting. Wow.
Mm-hmm. Unstable orbits, though. And then for rotating black holes, there's the ergosphere, outside the event horizon, too. Space-time itself is dragged around by the black hole's spin. Yeah, you literally can't stand still in the ergosphere relative to distant stars. Yeah. You're forced to rotate with the black hole. Theoretically, you could even extract energy from a rotating black hole there.
Okay, extracting energy. That's a whole other topic. But let's stick to basics. How do these things actually form? Where do they come from?
Well, the most common way we think they form is from the death of really massive stars.
Stars much bigger than our sun.
Yeah, significantly bigger. When they run out of fuel for nuclear fusion, the outward pressure stops. Gravity takes over.
And if the core left behind is massive enough.
Right. If it's above a certain limit, maybe 3 times the mass of the sun, roughly nothing can stop the collapse. Not electron degeneracy pressure, not neutron degeneracy pressure. It just keeps collapsing.
All the way down to a singularity forming a black hole.
That's the standard picture for stellar mass black holes.
But there's also mention of primordial black holes. Sounds different.
Very different origin story. The idea there is they could have formed fractions of a second after the Big Bang.
Right at the beginning, how?
In the very early universe, things were incredibly dense and hot. Tiny variations in density might have been enough for some regions to just collapse directly into black holes, purely from the immense pressure.
So not from stars collapsing, but from the conditions of the early universe itself. Could they be any size?
Theoretically, yes. From incredibly tiny, maybe Planck mass scale, up to perhaps hundreds of solar masses. It's still a theoretical idea, but a fascinating one.
Definitely. Okay, so they form either from stars or maybe the early universe. How do they get bigger? Do they just eat?
Essentially, yes. They grow by accretion, pulling in nearby gas, dust, stars, anything that gets too close.
And this forms those disks you mentioned, accretion disks.
Exactly. As matter spirals in, it gets compressed and heated up by friction and gravity. Really, really hot, millions of degrees.
And that's how we can see them, right? Not the black hole itself, but this superheated stuff falling in.
Precisely. These accretion disks can shine incredibly brightly, especially in X-rays. It's one of our main clues for finding black holes.
Okay. And what if two black holes find each other?
Then you get fireworks. Cosmic fireworks. They orbit each other, spiral inwards, and eventually merge.
They combine into one bigger black hole.
Yes. And this process releases an enormous amount of energy, not as light, but as gravitational waves. Ripples in space-time itself.
We'll definitely come back to those gravitational waves. Are these mergers important for how galaxies evolve? I think I read about supermassive black holes.
Very important. It's thought that these mergers are a key way that supermassive black holes, the ones found at the centers of most big galaxies millions or billions of times, the sun's mass actually grows so large. Our sources mention Omega Centauri as maybe a place where intermediate mass ones merge too.
So smaller ones merge, build up bigger ones. It's a cosmic construction process. But wait, I also read about Hawking radiation. Doesn't that mean black holes can shrink?
Yes. Stephen Hawking's incredible insight. It connects general relativity with quantum mechanics near the event horizon.
Quantum effects near a black hole.
Yeah. It's complicated, but the gist is that due to quantum fluctuations, pairs of virtual particles are constantly popping into existence and annihilating near the horizon. Sometimes one falls in and the other escapes.
And the escaping one carries energy away.
Exactly. From the outside, it looks like the black hole is emitting a faint thermal radiation, Hawking radiation. It means the black hole is slowly losing mass and energy.
Slowly. So they don't last forever, they evaporate.
Theoretically, yes. But the process is unbelievably slow for typical black holes. A solar mass black hole would take vastly longer than the current age of the universe to evaporate.
Okay, so not something we'd observe for stellar ones, but smaller ones.
Smaller ones evaporate faster, much faster. Our sources had some wild examples. A black hole, the mass of, say, a car would evaporate in like a nanosecond. A tiny burst of energy.
A nanosecond, and one with the human mass.
Almost instantaneously.
Yep.
Big flash. And the really tiny hypothetical ones, like 1 TV scale, gone in less than 10 to the minus 88 seconds, basically instantly.
Wow. Okay, that puts timescales into perspective. So we know what they are, how they form, how they grow, how they might die. But how do we know they're real, since we can't directly see them?
Right. It's mostly detective work, looking for their gravitational effects on things we can see.
Like stars orbiting nothing.
Exactly. At the center of our own Milky Way, Sagittarius A star, we've tracked stars whipping around an invisible point at incredible speeds. Their orbits only make sense if there's something incredibly massive and compact right there.
Millions of times the mass of the sun, packed into a tiny space.
That's really strong evidence for a supermassive black hole.
Okay, so stellar orbits. What about the accretion disks and X-rays you mentioned?
That's another key piece. We see binary star systems where one star is visible, but it's orbiting an invisible companion. And we detect intense X-rays coming from the system.
So the idea is the invisible companion is a black hole pulling gas off the visible star.
Precisely. The gas forms that super hot accretion disk, radiating X-rays before it falls in. Cygnus X1 was one of the very first and strongest candidates found this way. Still a classic example.
Makes sense. Indirect evidence, but pretty compelling. But then came the direct proof, right? Gravitational waves.
Oh, yes. That was truly game-changing. LIGO, the Laser Interferometer Gravitational Wave Observatory, in 2015, they made the first direct detection GW150913.
What did they detect?
They detected the ripples in space-time caused by two black holes, each about 30 times the mass of the sun, spiraling into each other, merging.
They actually measured space-time stretching and squeezing.
Yes! An unbelievable technological feat. It was direct proof that black holes exist, that they merge, and it was a stunning confirmation of Einstein's general relativity predictions about these waves.
I remember hearing those black holes were heavier than expected.
They were, yeah. Heavier than what astrophysicists thought typical stellar collapse would produce. That opened up new questions, too.
Wow. Detecting space-time ripples. Okay, and then there's the picture, right? The Event Horizon Telescope.
The EHT. Another incredible achievement. It's not a photo of the black hole itself because it's black, but
it's the silhouette, the shadow.
Exactly. By linking radio telescopes across the entire Earth, they created a virtual telescope the size of our planet. They were able to image the region right around the supermassive black hole in the galaxy M87.
And they saw that glowing ring.
They saw the shadow the event horizon casts on the glowing hot gas surrounding it. The light bent around the black hole. It matched the predictions of general relativity beautifully.
That image was amazing, just seeing that dark central region. And gravitational lensing, is that another way we look for them?
It is. A black hole's gravity is so strong it can bend light from objects behind it like a lens,
magnifying or distorting the background objects.
Yes. It's challenging to observe directly around, say, Sagittarius A, because the galactic center is so crowded and dusty. But astronomers are definitely looking for those lensing effects. It would give us more precise measurements of the black hole's properties.
It's like the universe provides all these clues, these different angles to study something inherently invisible. And that NASA simulation of falling in. What were the key takeaways from that visualization? It mentioned time behaving strangely.
Oh, definitely. The simulation really drives home the weirdness. Space-time distortion becomes extreme. Your view of the outside universe gets warped and squeezed.
And time dilation.
Yes.
Yeah.
As you get closer to the event horizon, time slows down for you relative to someone far away. The simulation gave that example. Orbit near the black hole for 6 hours, and you'd age about 36 minutes less than someone on a distant ship.
So time literally passes slower for you near that intense gravity.
Right. And for the distant observer watching you fall in, you'd seem to slow down more and more as you approach the horizon, getting redder and dimmer, appearing to take forever to actually cross it. Though for you falling in, you'd cross it without necessarily noticing anything special at that exact moment.
Freeze frame for the outside world, but normal passage for the unlucky person falling in. Wild. Okay, so we have all this evidence, this detailed picture. But it's not all figured out, is it? The sources mention some pretty big theoretical problems.
Oh, absolutely. Black holes are where our best theories, general relativity and quantum mechanics, seem to clash. They push physics to its limits and reveal gaps in our understanding.
Like the information paradox, what's the core issue there?
Right, the information loss paradox. So, quantum mechanics says information about a physical system can't be truly destroyed. It has to be conserved somehow.
Okay, information is conserved.
But general relativity suggests that when something falls into a black hole, the information about its specific state is lost behind the event horizon, gone forever from the outside universe.
And Hawking radiation doesn't solve it. Doesn't it carry the information back out?
That's the problem. Hawking radiation seems to be thermal, meaning it's random, and doesn't carry the specific information about what fell in. So, if the black hole evaporates completely via Hawking radiation, where did the original information go? It seems to have vanished.
Which violates quantum mechanics. So GR and QM give conflicting answers.
Exactly. It's a deep paradox. There are proposed solutions. Maybe the information is encoded in the Hawking radiation in some subtle way. Maybe it's stored in remnants. Maybe our understanding of horizons or locality is wrong. It's a huge area of research. Concepts like black hole complementarity, firewalls, the holographic principle, they all try to tackle this.
Okay, that's a major puzzle. And what about the singularity itself? You mentioned GR breaks down there.
That's the other big one. General relativity predicts this point of infinite density and curvature. But infinity in physics usually means the theory is incomplete, that it's missing something.
Like we need a better theory for those extreme conditions.
Precisely. We expect a theory of quantum gravity, one that successfully combines GR and quantum mechanics to resolve the singularity. Maybe it's not an infinitely sharp point, but some kind of quantum fuzziness or something else entirely.
And are there theories trying to do that? Like string theory?
Yes. String theory Loop quantum gravity and other approaches to quantum gravity are actively working on this. Some models suggest singularities might not form, or that event horizons might behave differently at the quantum level. You might even get rid of the classical idea of a sharp horizon.
So black holes are really pushing us towards a new understanding of gravity and quantum reality.
They absolutely are. They're like theoretical laboratories for exploring the most fundamental aspects of the universe. We also saw mentions of wormholes.
Ah, yes. Theoretically, certain types of black holes, rotating or charged ones, might contain connections to other parts of the universe or even other universes called wormholes.
But are they stable? Could you actually travel through one? Probably not. The theoretical solutions that allow traversable wormholes seem to require exotic matter with negative energy density, and they're likely incredibly unstable. So, fascinating mathematically, but probably not practical for interstellar travel, unfortunately.
Shame. Okay, so let's try and wrap this up. We've covered a lot. Black holes, regions of space-time with inescapable gravity.
Yep, predicted by general relativity, formed usually from massive stars collapsing, maybe also in the early universe.
They grow by sucking in matter, forming accretion disks, and they can merge, creating bigger black holes and sending out gravitational waves.
And we found them indirectly through their gravity's effect on stars and gas, and directly through gravitational waves and that amazing EHT image of M87's shadow.
But they still hold huge mysteries, right? Especially where gravity meets the quantum world, the singularity, the information paradox.
Exactly. They challenge our fundamental understanding of reality. We know a lot, but there's still so much more to figure out.
Okay, here's a final thought then, something for you, the listener, to ponder. Given that information seems to get lost inside black holes, or at least hidden in ways we don't understand, could black holes be more than just endpoints? Could they play some role in, the universe's way of processing or storing information on a cosmic scale, like nodes in some vast hidden network?
That's a really provocative question. It touches on deep ideas about holography and the nature of space-time itself. Definitely something to think about. And if this has sparked your interest, there's so much more to explore about general relativity, quantum gravity, and the ongoing search for answers about these incredible objects.